this video we talk about batch normalization. So let's get started. First of all, the table of contents. We talk about the bulk of the subject. What is block normalization? Covariate shift. What is covariate shift? Normalization and can it speed up learning? Experiments and conclusion, and how has it been used. Training deep neural network is complicated by the fact that the distribution of each layer's input changes during the training, just like this photo right here. This slows down the training by requiring lower learning rates and careful parameter initialization, and makes it notoriously hard to train models with saturating nonlinearities. We refer to this phenomenon as an internal covariate shift. Deep learning has dramatically advanced the state of the art in vision, speech, and many other areas. So in machine learning, we have an input where we do the feature extraction for it, and then we classify these data into till it comes an output. So the input here is an output if it's a car or not. But in deep learning, we have the input, we feature extraction plus classification at the same time. It happens at the same time, and we get the output if it's a car or not. We refer to the change in the distributions of internal nodes of a deep network in the course of training as internal covariate shift, eliminating it off as a promise of faster training. We propose a new mechanism which we call it batch normalization. So we take this internal covariate shift and turn it into a batch normalization. So what is covariate shift? Well, covariate shift is a specific type of dataset shift often encountered in machine learning. It is when the distribution of input data shifts between the training environment and the live environment. So as you can see, we have three positions here: training environment and live. It's a distribution between these two. So in covariate shift, we have internal covariate shift. We define internal covariate shift as the change in the distribution of network activations due to the change in network parameters during the training. After that, we reduce internal covariate shift. So to improve the training, we seek to reduce the internal covariate shift by fixing the distribution of the layer inputs X. As the training progresses, we expect to improve the training speed. What is normalization? What is batch normalization? Well, batch normalization is a method used to make artificial neural networks faster and more stable through normalization of the layers input by recentering and rescaling. So if you look at this photo, we have the first layer, which is the input layer, the axis that we talked about, and then we have the hidden layers that recenters and rescales to an output, which is the fifth layer here. How does this work? Well, it consists of a normalizing activation vectors from hidden layers using the first and the second statistical moments, mean and variance, of the current batch. This normalization step is applied right before or right after the nonlinear function. So if you look at the raw data or raw signal, you see that the knots are very complex, and it's very into each other. So we have a raw signal, high interdependency between distributions, slow and unstable training. But after transforming it into a normalized signal, so we notice that it is mitigated interdependency between distributions, and it is fast and stable training. Training. At each hidden layer, batch normalization transforms the signals as this algorithm follows. The layer first determines the mean and the standard deviation of the activation values across the batch using first and second. It is then normalizes the activation vector z by the power I with the 3. That way each neuron's output follows a standard normalization distribution across the batch. The results are clear-cut. Batch normalization layers make the training faster and allow a wider range of learning rate without compromising the training convergence. As you can see here, we have the inception, batch normalization baseline, etc. So experiment, activations over time to verify the effects of internal covariate shift on training and the ability of batch normalization to combat it. We considered the problem of predicting the digit class on the MNIST dataset. So this is without and with batch normalization. Here we have a nonlinear outline, as you can see, and with batch normalization it's very straight. So we applied batch normalization to a new variant of the inception network trained on the ImageNet classification task. And its MAC steps to 72.2%, and it is the max accuracy for the inception here. So in conclusion, we have presented a novel mechanism for dramatically accelerating the training of deep networks. It is based on the premise that covariate shift, which is known to complicate the training of machine learning systems, also applies to subnetworks and layers, and removing it from internal activations of the network may aid in training. If you look at this inputs, we have two inputs right here, and how they go into the hidden layers, and then we get a linear output with batch normalization. Thank you. These are the references, and thank you for watching this video.